Module D, General Gatekeeping Strategies. The main goal of this module is to discuss key principles and key methods for constructing gatekeeping procedures that can be applied in a very general setting. And this is why I'm going to refer to this class of procedures as general gatekeeping procedures. As you remember from Module C, this is where I introduced a class of advanced multiplicity problems with parallel gatekeepers. And a parallel gatekeeper is characterized by the fact that to pass this family of hypotheses and proceed to the next family of hypotheses, it is sufficient to reject a single hypothesis within the gatekeeper. If we impose this kind of gatekeeping restrictions on the families of interest, as we discussed, we can construct gatekeeping strategies based on non-parametric or chain-based or potentially more powerful semiparametric component procedures, such as the Hogberg procedure. In this module, we're going to consider a broader family of gatekeepers. When I introduced them in Module B, I referred to them as general gatekeepers. It is a more complex type of binary relations among the individual hypotheses included in different families. But the great news here is that despite this complexity of logical relationships among the hypotheses in a multiplicity problem, there is a very general method known as the mixture-based method that enables clinical trial sponsors to build gatekeeping procedures that, first of all, they account for these logical relationships, and secondly, of course, that's the main objective of any gatekeeping procedure. These gatekeeping procedures control the overall type 1 error rate across the families. So they control the global family-wise error rate. And these procedures can be constructed from building blocks from the appropriate clinically meaningful component procedures that could be non-parametric procedures or semi-parametric or even fully parametric procedures. So as you can see, there's only one section in this module, that is section D1, General Gatekeeping Procedures. And this section is going to focus on a general class of procedures that can be constructed using the mixture method, and we will refer to them as mixture-based gatekeeping procedures. Section D1, General Gatekeeping Strategies. To define a general setting that will be considered in this module, we're going to return to example 3 that was introduced in Module A. This is the clinical trial example based on a phase 3 clinical trial in patients with acute schizophrenia. The multiplicity problem arising in this clinical trial example is a bivariate multiplicity problem in the sense that there are two sources of multiplicity, and the resulting 4 hypotheses of interest based on 2 clinical endpoints and 2 dose placebo comparisons are grouped into 2 families as shown on the slide. The primary family, or family 1, includes the primary endpoint tests, and these are the tests for testing the hypotheses H1 and H2, and these are the hypotheses that are formulated in terms of comparing each dose in this clinical trial, the low dose or the high dose versus placebo on the primary endpoint. And I would like to quickly remind you that the primary endpoint in this clinical trial was based on the change from baseline to the end of the trial in the PANSS total score. PANSS here stands for the Positive and Negative Syndrome Scale. And the secondary endpoint tests will be put in the second family, or family 2, which includes the hypothesis H3 and H4, and as explained on the slide, those hypotheses are the hypotheses of no difference between the low dose and the high dose versus placebo, respectively, and those tests are based on the key secondary endpoint in this trial, which was the CGI-S score. CGI-S here is the Clinical Global Impressions Severity scale that is commonly used as a key secondary endpoint in schizophrenia trials. The diagram that you see on the slide defines the clinically relevant logical restrictions in this phase 3 clinical trial. We examined these logical relationships back in Module B, and we said at that time that a dose placebo test on the key secondary endpoint would be relevant only if a significant treatment effect was established for this same dose on the primary endpoint. And these logical relationships are visualized on the slide using arrows. You can see that there are the arrows connecting the hypotheses H1 and H3, and secondly the hypothesis H2 and H4 on the right hand side. And according to these logical restrictions, as shown at the bottom of the slide, the hypothesis H3 can be tested only if H1 is rejected, and likewise H4 can be tested only if H2 is rejected, which immediately implies that the primary family here is not a parallel gatekeeper, because as we said multiple times in Module C, with a parallel gatekeeper, the hypothesis H3 would be testable if any of the primary hypotheses were rejected, which is not the case here. In this case, we say that family 1 is a general gatekeeper for family 2. And we're interested here in formulating an approach that will enable us to set up gatekeeping procedures for this and, of course, much more complex problems that could involve general gatekeepers. On this slide, I'm going to say a few words about the mixture-based methodology that I mentioned earlier in this module. This is a very general approach that was introduced a few years ago in 2 papers that were written by Professor Ajit Amhani and myself. This method, as I said, is known as the mixture-based methodology, and it provides us with a set of powerful tools for constructing gatekeeping procedures that are consistent with arbitrarily complex logical relationships among the hypotheses in a multiplicity problem. So theoretically speaking, a mixture-based gatekeeping procedure can be set up for any multiplicity problem with several families of hypotheses. This includes, for example, problems with parallel gatekeepers that we discussed in Module C, and in fact, it can be shown quite easily that the more powerful semiparametric gatekeeping procedures, for example, the Hogberg-based gatekeeping procedure that we discussed, are actually a special case of general mixture-based gatekeeping procedures that we're going to focus on in this module. And for this reason, due to this very flexible nature of the mixture-based methodology, it has found multiple applications to dozens of phase 3 clinical trials. And what we emphasized in our papers is that this is a general approach, and it can be used with any combination of multiple testing procedures or component procedures, as we typically call them. That includes non-parametric components, semi-parametric components, or fully parametric components, depending on the amount of distributional information that is available to us when we are about to begin constructing a gatekeeping procedure. And the way it works in very simple terms, what we're going to do here is we're going to begin with a set of building blocks, or as I call them, component procedures, and we're going to construct a gatekeeping procedure that respects the predefined logical relationships, and it ultimately protects the overall error rate across the families. And I'm going to explain in a few minutes why we decided to use this term mixture in the context of multi-family multiplicity problems, and that's because there is actually an interesting direct analogy here with mixtures of distributions. One of the main points I emphasized in the previous slide is that the mixture-based methodology can be used with any set of logical relationships in a multiplicity problem. And to give you an idea of how it works, we're going to look at a very simple multiplicity problem with 2 families of hypotheses, which is defined on the slide. This is conceptually very similar to a two-family multiplicity problem that we discussed back in Module C. We're going to assume that in family 1 there are k null hypotheses of interest. We're going to introduce, just like we've done before, the index set denoted by n1. That's the set of hypothesis indices included in the primary family. We're going to predefine a component procedure. Let's refer to it as procedure 1 for now. It is important to make sure that this is a separable procedure that provides local alpha control within this family. We discussed in Module C why it is so important to work with separable procedures such as the truncated Hagberg, because that enables us to transfer alpha from the first family to the second family. And in the second family here we can assume, just for the sake of simplicity, this is not an important assumption, that there are also k null hypotheses. This would be k secondary null hypothesis, and we can also define the index set in the secondary family. It will be denoted by n2, and there's also a pre-specified procedure 2 that provides local alpha control within this family. In this case, we don't have to worry about the separability condition. We can use, for example, the regular Hagberg procedure because this is the last family in the sequence. Now, to figure out how to incorporate, as I said, arbitrarily complex logical relationships among the hypotheses of interest into the testing algorithm, it is important for us to realize that those logical relationships need to be defined at the hypothesis level rather than at the family level. That is really the key point on the slide, because if we go back to simple logical relationships or logical restrictions that we have discussed before, including serial gatekeepers or parallel gatekeepers, we need to realize that those restrictions operate at the family level. For example, with serial restrictions, we impose the following condition, that all null hypotheses in the entire family 2 would be testable if all null hypotheses in family 1 are rejected. And with parallel gatekeepers, the restrictions are also applied at the family level. We're not referring to the individual hypothesis, we also refer here to hypotheses in family 2 or in family 1. They're considered as if they are treated together, not separately. And as you can see, when we formulate those serial or parallel gatekeeping procedures, we are not going to. So to summarize, when we formulate serial or parallel gatekeeping relationships, we are referring to the entire family rather than to the individual hypothesis. And on the next slide, we're going to discuss how to expand this approach to a more general setting to enable more complex logical relationships. This takes us to a discussion of the so-called restriction functions, and I know that there's a lot of mathematical notation on the slide, but I promise I will give an example to illustrate the key ideas presented here on the next slide. So let's take a closer look at the ideas, concepts presented on this slide. The general idea here is that logical relationships among null hypotheses in families 1 and 2 can be specified using binary restriction functions. These are functions that establish binary relations between the primary hypothesis and the secondary hypothesis, and this ultimately enables us to define logical restrictions at the hypothesis level rather than at the family level. And the restriction function, as you see on the slide, it is denoted here by L, depends on the index I, and that is the index of a secondary hypothesis that we're interested in testing. And this function also depends on the index set I1, and that is the set of outcomes, or in other words, the set of significant tests or rejected hypotheses in family 1. If this restriction function is equal to 1, then the hypothesis HI will be testable, which means that this hypothesis will be examined and the hypothesis test will be carried out. But if the restriction function is equal to 0, the hypothesis H1 will not be testable. This means that it will be accepted without testing. It is no longer clinically relevant. Now, to summarize, you can see at the bottom of this slide, once we have the appropriate restriction functions defined that correspond, of course, to the predefined clinically relevant logical relationships among the hypotheses, then those functions can be applied in a very straightforward way. The first step will be to determine which individual hypotheses are rejected in family 1, and this set will be denoted by R1, as you can see at the bottom of the slide, and then each individual hypothesis in family 2 will be classified as testable if the restriction function is equal to 1, and if the restriction function is equal to 0, then the hypothesis will not be testable. It will be accepted without testing, as we said a minute ago. Here's a simple illustration that shows you how the key ideas behind the restriction functions can be applied to example 3. As I said in slide 10, our goal here is to define a binary relation among possible outcomes in the primary family in each individual secondary hypothesis. The outcomes in the primary family, or in other words, sets of rejected null hypotheses in family 1, are shown in the leftmost column in this table. There are 4 possible outcomes. First of all, both primary hypotheses are rejected, and then H1 is rejected and H2 is not rejected. The third outcome is that H2 is rejected and the other hypothesis is not rejected. And finally, the last outcome is empty, which means that there are no rejections in the primary family. The next column shows the secondary hypothesis. In this case, there are only 2 secondary hypotheses, H3 and H4. And the column on the right-hand side defines the binary relation. What this means is that for every set of rejected primary hypotheses and every secondary hypothesis, we can state whether or not this second hypothesis is testable. For example, if we take a look at the top row in the table, we see that in this particular case, both hypotheses in the primary family are rejected, and then H3 will definitely be testable because the corresponding secondary endpoint test is clinically relevant. But by contrast, when we look at the third row in the table, that is the setting where only H2 is rejected. H1 is not rejected, which means that a significant effect is established on the primary endpoint only at the high dose, but there is no evidence of a significant effect at the low dose. So as a direct consequence of that, H3 is no longer testable because this hypothesis corresponds to the low dose test on the secondary endpoint, and this test is not meaningful anymore. So this hypothesis H3 should be accepted without spending any alpha on the corresponding test. We have talked fairly quickly about the new approach to defining logical restrictions in complex multiplicity problems. This can be accomplished using a family of restriction functions, and now we are ready to introduce the general mixture-based methodology, which is once again a framework for constructing gatekeeping procedures for clinical trials with hierarchical objectives. And that defines multiple families of hypotheses. And when we use the term mixture in this context, we make an analogy with a mixture of data distributions. In general, as you remember, when we specify a mixture distribution, we need to first specify the component distributions, and then we define a mixing distribution. So to give a quick example, we can think of a mixture of 2 normal distributions, and the mixing distribution may be a simple Bernoulli distribution, so that, for example, half of the time we sample from the first normal distribution, and the remaining time we're going to sample from the second normal distribution. And Likewise, when we define a mixture-based gatekeeping procedure, as you can see on the slide, there are three ingredients I should say, that need to be specified. First, we define the component procedures, procedure 1 and procedure 2. Each procedure will be applied within the corresponding family, and it's going to be set up in such a way that it guarantees local error rate control. For example, as we said a few minutes ago, the truncated Hogberg could be applied within family 1, and the regular Hogberg procedure could be applied within family 2. And also we need a mixing function. The mixing function here plays a very important role because it helps glue the two component procedures together, so to speak. This mixing function ensures that the overall or global type 1 error rate will be protected across the two families of hypotheses. We have said many times before, it is not sufficient in the context of confirmatory clinical trials when we have multiple families of null hypotheses. It is not sufficient to guarantee local error rate control within each family. The current regulatory requirements state that our goal is to provide global overall error rate control with respect to all hypothesis index complex multifamily multiplicity problem. What we defined on slide 12 was essentially a general outline. It's a general set of rules for constructing mixture-based gatekeeping procedures, and I think it will be very helpful to give a few examples here. What we're going to do now is to consider several scenarios with different types of building blocks or different types of component procedures applied within each family, and also different types of mixing functions that are used to combine the inferences across the families. We're going to compare and contrast component procedures and mixing functions that utilize different amounts of distributional information. For example, we can think of component procedures and mixing functions that fully utilize all available information and they fully take into account the between family and within family correlations. Or on the other hand, we can think about another extreme when that distributional information is completely ignored. Using the schizophrenia trial example, which was example 3, on this slide, we're going to define the most basic type of a mixture-based gatekeeping procedure. We can think about this gatekeeping procedure as a non-parametric gatekeeping procedure that completely ignores the relevant clinical information that comes in the form of distributional information, the information about the joint distribution of the hypothesis test statistics. For example, as you see on the slide, we can apply the bond-forming procedure within the primary family, also the bond-forming procedure within the secondary family, in which case we're not going to account for the within family correlations. And we're also going to consider a non-parametric mixing function, which means that we're going to apply the same approach. We're going to ignore the between family correlations. This slide presents a visual summary of the choices that we discussed on slide 13. As you remember, we defined kind of an extreme case of a fully non-parametric mixture-based gatekeeping procedure that employed a non-parametric procedure, the bond-forming procedure within the primary family, and that's what you see presented graphically on this slide. The primary family includes the hypothesis H1 and H2. Their distribution information, could be summarized here, for example, using the correlation coefficient between the hypothesis test statistic. With the bond-forming based approach, this within family correlation will be ignored. Likewise, when we step down and look at the hypothesis included in the secondary family H3 and H4, we're going to apply also the bond-forming procedure, which means that the within family correlation will be ignored, and the inferences in the primary family and in the secondary family will be combined, will be glued together using a non-parametric or bond-for-any-based mixing function. So at the end of the day, we end up with a bond-for-any-based gatekeeping procedure that once again ignores the within-family correlations. It ignores the between-family correlations. This is obviously a very inefficient way of performing a multiplicity adjustment in this problem. It is inefficient to ignore relevant distributional information. And on the next several slides, we're going to discuss alternative ways of selecting the building blocks of a mixture-based gatekeeping procedure that could be used in this particular trial example. As we said, a bond-for-any-based gatekeeping procedure is quite inefficient, and we could potentially consider a gatekeeping procedure that utilizes all available distributional information. We can suppose, for example, that we know the joint distribution of the 4 hypothesis test statistics in this multiplicity problem at the design stage, which means that the pairwise correlation coefficients are known to us. They don't need to be estimated. We know the true values of those parameters at the time when we're going to design the trial and specify the multiplicity adjustment. In this case, it will be most sensible to select the component procedures that take the within-family correlations into account, and this can be accomplished by applying a parametric procedure within each family. For example, on this slide, just as an example, I'm proposing to apply the Dunning procedure within the primary family and also the Dunning procedure within the secondary family. And since we know the joint distribution of the test statistics, the between-family correlations can also be taken into account. And to be able to do this, we need to specify a parametric mixing function. This slide presents a diagram that captures the assumptions and the choices we made a minute ago. The main difference between this slide and the slide that defined a non-parametric mixture-based gatekeeping procedure is that here we're applying a parametric procedure, the Dunning procedure, within the first family, because we would like to be able to take advantage of the fact that we know the within family correlations, and for the same reason we're going to apply a parametric procedure at the bottom of the slide within the secondary family, and then we're going to combine the inferences between the two families utilizing a parametric mixing function. The resulting parametric gatekeeping procedure will account for the within family and between family correlations, and this procedure will result in the most efficient multiplicity adjustment in this clinical trial example. But the thing here is that we cannot justify this assumption that the joint distribution of the hypothesis test statistics is fully known to us at the design stage. I'm referring specifically to example 3, and this means, as I will explain on the next slide, that we will need to modify our choices of the component procedures and the mixing function. This approach that would be most sensible in the context of example 3 based on the schizophrenia clinical trial is that we're going to first recognize the fact that the joint distribution of the test statistics is unknown to us, and as due to the fact that we don't know the true correlation between the primary and secondary endpoints. Yes, we can always estimate that correlation coefficient from relevant historical data, but the true correlation, and that's the most important point here, the true correlation remains unknown to us. And by contrast, the joint distribution of the hypothesis test statistics within each family is known at the design time. For example, and we've said this multiple times before, including part 1, if we deal with a balanced design with the same number of patients randomly allocated to the 3 trial arm, in this clinical trial example, it is easy to show that the 2 pairwise correlations, the low dose versus placebo and the high dose versus placebo, both of those pairwise correlations will be equal to 0.5. This means that the within family correlations are known, but the between family correlations are unknown. In this case, we are forced to use a non-parametric mixing function, but within each of the two families in this multiplicity problem, we could do better than a basic non-parametric procedure. For example, as you can see on the slide, we could consider applying a semi-parametric procedure within the primary family, a Hogberg type procedure, and also a semi-parametric procedure within the secondary family. And you notice that I said a Hogberg type procedure. And the reason for that is that we cannot use the regular Hogberg procedure in family 1. We must switch to a separable or a generous component procedure. For example, the truncated Hogberg, but in family 2, the regular Hogberg procedure can be safely applied. This diagram defines visually the three ingredients of the corresponding mixture-based gatekeeping procedure. We can refer to it as the Hogberg-based gatekeeping procedure. It is quite similar to the diagrams that we have looked before. The only difference between this diagram and the other two diagrams that we have examined is that here we're going to specify a semi-parametric component within the primary family, a semi-parametric component within the secondary family, and they will be glued together using a non-parametric mixing function. And that is because, once again, we do not know the between family correlation coefficient. So, to summarize, the three building blocks would define a semi-parametric gatekeeping procedure that accounts for the within family correlations, but we cannot account, once again, for the between family correlation because the correlation is unknown to us. To quickly summarize what we have discussed, we have talked about the possibility of employing a generally inefficient non-parametric gatekeeping procedure or a very efficient fully parametric gatekeeping procedure in example 3. Unfortunately, in this particular case, an efficient multiplicity adjustment based on a parametric gatekeeping procedure cannot be utilized. But it could be potentially considered in other multiplicity problem where the joint distribution of the hypothesis test statistic is fully specified. What is important for us to remember is that the general mixture-based framework is very flexible, and it enables us to incorporate all the relevant information about the multiplicity problem at hand. That includes distributional information. And as an alternative to the non-parametric or parametric gatekeeping procedures, we have considered a semi-parametric Hogberg-based gatekeeping procedure. This procedure is the most meaningful approach to multiplicity adjustment in example 3, and this Hogberg-based procedure will be constructed to protect the overall type 1 error rate in example 3 from the three building blocks that are defined on the slide. Once again, the truncated Hogberg in family 1, the regular Hogberg procedure in family 2, and a non-parametric mixing function needs to be applied because the between family correlation is unknown. Mixture-based gatekeeping procedures. We're now ready to discuss the process of setting up mixture-based gatekeeping procedures. Certain details and derivations are quite technical, and I would like to point out that it may take a long time to go through those details. For this reason, we're not going to dig too deep and will remain at a fairly high level and will aim for conceptual understanding. I would also like to point out very quickly that the original or standard mixture method that was developed prior to 2011 and recently we have published a few papers to extend the standard mixture method, which leads to improvements in specific settings or specific multiplicity problems that commonly arise in phase 3 clinical trials. This includes, for example, problems with several sequences of hypotheses that are tested sequentially within each sequence. I will give an example in a few minutes, but for now I would like to simply quickly mention that if we focus on a certain class of multiplicity problems, it turns out that the standard mixture method can be extended to build more powerful gatekeeping procedures. Specifically, we showed that the so-called modified mixture-based gatekeeping method is more powerful than the standard method, and in addition, as I will explain in a few minutes, it has an attractive feature. It supports stepwise testing algorithms, and more recently we have introduced a class of enhanced mixture-based gatekeeping procedures that turned out to be uniformly more powerful than the modified mixture-based gatekeeping procedures. To define a general approach to setting up mixture-based gatekeeping procedures, we're going to begin with the fundamental fact that to protect the overall type 1 error rate in a multiplicity problem, the mixture method relies on the closure principle. I introduced the closure principle in part 1 of this online course, and I explained at that time that multiple testing procedures that we're going to discuss in part 1 as well as in part 2, they're all in fact derived using this powerful principle. So mixture-based gatekeeping procedures are no exception. And since the semiparametric parallel gatekeeping procedures from Module C are a special case of mixture-based gatekeeping procedures introduced in this module, those parallel gatekeeping procedures are also based on the closure principle. It's just when I introduced them in Module C, I decided not to emphasize this fact to avoid potential confusion. So let's now take a look at the specific steps we will need to take to define a general closed testing procedure, and I'm going to explain how this process needs to be slightly modified to enable a mixture-based approach that efficiently takes into account arbitrarily complex logical restrictions among the hypotheses. Using example 3 as an example, step number 1 would be to define a closed family of hypotheses, which includes all possible intersections of the 4 hypotheses of interest that are once again denoted by H1 through H4. After that, in step 2, we're going to define a set of alpha-level local tests for all intersection hypotheses in the closed family. And finally, step 3 would be to define decision rules for each individual null hypothesis. And this is something that would be applicable to a very broad class of closure-based testing procedures. We can reject, according to the closure principle, we can reject a null hypothesis only if all intersection hypotheses containing this null hypothesis are rejected by their respective local test. That is the mechanism that provides family-wise error rate control, and the same mechanism can be used to ensure global family-wise error rate control whenever the multiplicity problem of interest includes several families of hypotheses. This slide provides a visual summary of the closed family of hypotheses in example 3, which once again includes 4 hypotheses of no effect. This diagram, as we said on the previous slide, includes all possible intersections of those 4 hypotheses. It begins at the bottom with the boxes that include just one hypothesis at a time. As we're moving up this diagram, we can see two-way intersections and then three-way intersections, and finally at the very top of this diagram we see a four-way intersection. That's the intersection of all hypotheses considered in this problem. And a good analogy to make here would be to compare this diagram with a analysis of variance or ANCOVA model that could be used whenever we have 4 different factors. If we consider a saturated ANOVA model, it would include the main terms that would correspond to the individual hypotheses shown at the bottom of this diagram. This ANOVA model would also include two-way interactions, and they roughly correspond to those two-way intersections. Three-way interactions would correspond to the three-way intersections, and the box at the very top of this diagram would be an example of a four-way interaction or a four-way intersection. Step 2, as we said, would involve defining local tests. For each individual intersection in the diagram on slide 23, we must define an alpha level local test. And then the inferences from those local tests will need to be combined according to the closure principle to be able to support inferences for the individual null hypothesis. Here, just for the sake of illustration, I'm going to show you how to set up a Bonferroni-based gatekeeping procedure. With a Bonferroni-based approach, the local tests for the individual intersection hypotheses are defined in a very straightforward way. They are simply based on minimum p-value tests. And by the Bonferroni inequality, it's very easy to show that each one of those local tests is in fact an alpha level test. And therefore, when we apply the closure principle, the Bonferroni-based procedure is going to control the family-wise error rate globally at alpha. And I would also like to point out very quickly that this is just a procedure that will be used for general illustration. It is not going to account for logical relationships yet. We're going to explain in just a few minutes how to introduce logical relationships. So we're back to the diagram that included all possible intersections of the individual null hypothesis. And now within each one of those boxes we see additional information. That additional information defines the local test for each individual intersection. For example, beginning with the box at the very bottom, we're going to use a Bonferroni type minimum p-value test, which means that this intersection hypothesis, the four-way intersection hypothesis, will be rejected if the minimum of the four p-values is less than or equal to alpha 4. The same conceptually similar approach will be applied to the other intersection hypothesis. The minimum p-value test will be slightly modified. It's going to account only for the hypotheses included within each individual intersection, but the alpha level will remain the same. As you can see throughout this diagram, each local p-value is compared to alpha over 4, including even the boxes displayed at the bottom of this diagram. And the reason for that is because we're using a conservative Bonferroni-based approach. In general, when we consider other more powerful approaches to constructing local tests, for example, semiparametric or parametric procedures, the alpha levels used within each box will be appropriately adjusted. Slide 26 illustrates step 3. We now need to define decision rules for the individual null hypothesis, and I'm going to use here, for example, a set of decision rules for the hypothesis H1. As you can see at the bottom of the slide, the hypothesis H1 will be rejected only if all highlighted or orange boxes would be rejected. And the reason I highlighted some of those boxes that are shown in the original orange color is because these are the intersections that include the hypothesis of interest. They include H1, and the other intersections that do not include H1 are grayed out in this diagram. In this particular case, to be able to formulate a decision rule, a rejection rule for the hypothesis H1, we do not really care about those grayish boxes. We just need to make sure that all of the orange, the highlighted intersection hypotheses, are rejected by the appropriate respective local tests. What we have discussed so far is a general approach to constructing a closure-based set of decision rules. And as I emphasized a few minutes ago, this is an example of a basic Bonferroni-based gatekeeping procedure that completely ignores the relevant logical restrictions. It is now important for us to discuss what it takes to incorporate clinically relevant logical restrictions, and the general process is defined on this slide. The key here is to modify the local tests. In each individual local test, and by that I mean the test which is applied within each individual intersection hypothesis, needs to be modified to ensure that the resulting gatekeeping procedure is consistent with logical restrictions. The way it is done is that instead of looking at the original local tests, we're going to define the so-called restricted local tests based on the pre-specified restrictions. I'm going to explain how it is done on the next slide. The logical restrictions that would be most relevant in example 3 were discussed at the beginning of this module. We said at that time that in the context of this multiplicity problem, it is most relevant, most meaningful to apply the logical restrictions defined at the top of the slide. Specifically, H3 can be tested only if H1 is rejected, and likewise H4 can be tested only if H2 is rejected. To incorporate this set of logical restrictions and define appropriate restricted local tests, all we need to do is to apply a fairly simple set of modifications. If we look at an intersection hypothesis and it happens to contain H1 and H3, then the p-value P3 will be removed from the local test. This is done to make sure that if H1 is not rejected, then H3 would not be testable, which means that it would be accepted without testing. And the same principle would be applied to an intersection hypothesis that contains H2 and H4 simultaneously. To end up with a gatekeeping procedure that is consistent with the predefined logical restrictions, we need to remove the p-value P4 from the local test. This diagram defines a set of decision rules based on restricted local tests, and here, for the sake of simplicity, because this diagram is already getting quite complicated, what I have done is I have simply kept the p-values within each box that should be used to define a local test for that intersection that would be consistent with the pre-specified logical restrictions. For example, beginning with the box at the top of this diagram, this is the intersection hypothesis that includes H1, H2, H3, and H4. So using the rules for defining restricted local tests that were shown on slide 28, we are required to remove the p-value P3 and P4 from the local test. This is done to ensure, once again, that the hypothesis H3 cannot be possibly rejected unless H1 is rejected, and also H4 cannot be testable unless H2 is rejected. The same principle is applied to the remaining intersection hypotheses in this family, and as a result, we end up with a set of decision rules that fully respect the predefined logical restrictions. This is the last slide in this fairly short section on the closure principle. As I said before, it may be counterproductive to spend too much time on the technical details. After all, we have software tools that can be used to run closure-based calculations. I feel that it's much more important to understand the general set of principles, and from this perspective, let's take a look at this diagram. Instead of using a Bonferroni-based local test within each intersection hypothesis, we will consider here a general local test. It is denoted by T. It is a function of appropriate p-values within each box in this diagram, and this test can be set up to account for the available distributional information. This could be potentially a parametric local test based on the Dunning procedure, or this could be a semi-parametric local test based on the Hogberg procedure. The main message here is that using an appropriate local test, we can compute a local p-value for each intersection in this closed family, and we will then compare it to alpha. The resulting gatekeeping procedure would be an example of a mixture-based gatekeeping procedure that, of course, controls the overall alpha. This is by construction, by the closure principle, and in addition, it accounts for relevant distributional information. This is accomplished by using an appropriate local test within each box within each intersection in this closed family. And finally, by construction, by using the restricted local test, this procedure is going to incorporate the clinically relevant logical restrictions. Stepwise testing algorithm. An important feature of the modified mixture method is that it supports a stepwise testing algorithm. Normally, a multiplicity adjustment is applied using rules based on the closure principle, and multiplicity adjusted p-values are computed using also the closure principle. And a stepwise testing algorithm may be desirable from a practical perspective, since it generally facilitates the interpretation of the decision rules, and it facilitates communication of the results to the project teams and regulatory reviewers. In this section, I will define a stepwise testing algorithm for a modified mixture-based gatekeeping procedure using example 3. This slide shows a familiar diagram for example 3 that places the individual null hypotheses of interest by family. They're organized vertically by family. The top two hypotheses H1 and H2 are included in the primary family. The bottom two hypotheses H3 and H4 are included in the secondary family. In addition, we can think about two different sequences of hypotheses. This would be an example of a multiplicity problem with two sequences of hypotheses. They are shown on the slide and they're labeled sequence 1 and sequence 2. And as you can see, within each sequence, the hypotheses are tested sequentially. For example, within sequence 2, we begin with the hypothesis H2 and proceed to H4 only if the hypothesis H2 is rejected. This would be an example of a multiplicity problem where, using the modified mixture method, we can construct an attractive stepwise testing algorithm. To illustrate the stepwise testing algorithm in example 3, we're going to assume a set of raw p-values that are defined in this table. I would like to clarify that these are one-sided p-values, and our objective is to construct a testing algorithm for a Hogberg-based gatekeeping procedure, which is derived using the modified mixture method. And this procedure is going to aim at controlling the global family-wise error rate at a one-sided alpha of 0.025. Mostly to help us refresh our memory, on this slide I'm going to define the component procedures that will be used in this Hogberg-based gatekeeping procedure. Within family 1, as we have said many times before, we're going to apply the truncated Hogberg procedure. For the sake of concreteness, we're going to say the truncation parameter gamma 2.7. Within family 2, we will either utilize the regular Hogberg procedure. That would be the case, of course, if both hypotheses are rejected in family 1, and therefore, based on the predefined logical restrictions, both hypotheses in the secondary family would be testable. However, it's possible that in family 1, only one test is significant, the other test is not significant, in which case, again, based on the predefined logical restrictions, only one hypothesis would be of interest to us in the secondary family, in which case, instead of using the regular Hogberg procedure, it will be sufficient to apply a basic univariate test. There will be no other sources of multiplicity within family 2 in this particular case. In the next several slides, I'm going to go over the underlying decision rules. These slides are actually very similar to the corresponding slides that I used in module C when we were going over the underlying decision rules for the Hogberg-based parallel gatekeeping procedure. In this case, essentially the same set of rules will be applied to set up a Hagberg-based procedure, but in a more general setting, because here we have a general gatekeeper instead of a parallel gatekeeper. But the great news is that conceptually the testing algorithm is actually quite similar. So back to family 1, where we said that we're going to apply the truncated Hagberg procedure with a predefined truncation parameter defined by gamma. In this case, the hypothesis will be tested at the full level alpha, which means that the local level denoted by alpha 1 will be set to alpha. And just to remind you how we typically carry out the truncated Hagberg test, if we assume that the ordered p-values are denoted by p1 and p2 using the standard parenthetical notation to define the smaller of the two p-values and the larger of the two p-values, then both hypotheses will be rejected if the larger p-value is less than or equal to 1 plus gamma times alpha over 2. If this condition is not satisfied, if the larger p-value is actually above that threshold, then the truncated Hagberg procedure is going to step down, examine the smaller p-value, and the corresponding hypothesis, as you see on the slide, will be rejected if that smaller p-value is less than or equal to alpha over 2. The next aspect of the gatekeeping procedure that we will need to discuss would be a set of rules for transferring the alpha from the first family to the second family. We refer to them, as we did in Module C, as the alpha propagation rules. There are only 3 potential outcomes of interest that could be observed in family 1. They're all listed on the slide. The first one is when no null hypotheses are rejected in family 1. In this case, just like we did in Module C, we're going to apply the error rate function of the truncated Hagberg procedure from the first family. This error rate function is denoted by E, and this is a function of the set of accepted hypotheses in the first family. In this very first setting, when both hypotheses are accepted, the index set includes the indices 1 and 2, and applying the same formula that we used in Module C, we can easily show that no alpha will be available for testing the hypotheses in the secondary family, because the local alpha level used in family 2, it is denoted by alpha 2 in this case, is simply equal to 0. That is to be expected, because if we fail to reject any null hypothesis in the primary family, of course the secondary hypotheses are no longer meaningful. The second outcome of interest here is the case where exactly one null hypothesis is rejected in family 1. In this case, the index set A1 is equal to either 1 or 2, depending on which hypothesis is accepted in family 1. And it's easy to show using again the error rate function of the truncated Hagberg procedure. It's easy to show that alpha 2, the local level in family 2, is equal to 1 minus gamma times alpha over 2. And in the last case listed on the slide, when the index set A1 is empty, all of the alpha will be transferred to the secondary family. Using this information, we are now ready to go over this specific numeric example, and we're going to use a set of diagrams that are once again quite similar to the diagrams that we utilized in Module C. I think they are quite appealing visually. They help us visualize the decision rules applied in family 1, which is this slide, and then in family 2 on the next slide. We're going to begin with the alpha level set to 0.025. That is the one-sided alpha level that will be applied to the primary family. And using the rules that are shown at the bottom of the slide, And this is all based on the decision rules that we defined on slide 36. It is easy to verify that with the truncated Hogwarts procedure and gamma set to 0.7, the first hypothesis in this family, H1, will be rejected, but H2 cannot be rejected, it will be accepted. That means that, first of all, we're going to proceed to testing the hypothesis in the secondary family. And secondly, we need to figure out how much alpha can be carried over to the secondary family. This can be used the formula that comes from slide 37. The alpha level, alpha 2, the local alpha level for the secondary family, is equal to 1 minus gamma times alpha over 2. And in this particular case, it ends up being a relatively small value, 0.00375. That is a function of the fact that gamma was set to a fairly high level in the primary family. Now continuing to the secondary family, or family 2, we will get to carry out a univariate test. And that is due to the fact that we pre-specify a set of clinically relevant logical restrictions that remove the hypothesis H4 from consideration because H2 was not rejected in the first step of this procedure, and therefore the available alpha level of 0.00375 will be applied in a univariate testing manner to the only testable hypothesis in this secondary family. That's the hypothesis H3, and we can easily verify here that since the p-value corresponding to that hypothesis, the p-value is equal to 0.0022, is below the local alpha level of 0.00375, we can come to a conclusion that H3 is rejected, and once again H4 is not even tested because this hypothesis is no longer relevant. That's one of the key advantages of constructing meaningful logical restrictions. They prevent us from spending, or I should say wasting alpha on the hypotheses that are no longer meaningful. In this case, instead of splitting the alpha potentially between H3 and H4, we channel that alpha, if you will, towards the only meaningful hypothesis in the secondary family. The last section in this module covers software implementation issues. Beginning with software implementation options in SAS, I would like to mention that a custom macro that we used in Module C, the same custom macro called the mixed gate macro, could be used to provide multiplicity adjustments based on a fairly broad class of general mixture-based gatekeeping procedures. I'm going to give a quick example to show how this mixed gate macro could be used to implement the Hogberg-based gatekeeping procedure in example 3. Here we're going to follow the same outline, the same structure that we used in the numeric example a few minutes ago. Within the primary family, the truncated Hogberg procedure with the gamma set to 0.7 will be utilized. In the secondary family, the regular Hogberg procedure or a univariate test will be applied. We're going to assume the same set of p-values in family 1 and in family 2. This slide shows the code that needs to be run in SAS to invoke the mixed gate macro and perform a multiplicity adjustment based on this general gatekeeping procedure. We begin by defining the data set called EX3. It stands for example 3. This is the data set that specifies all of the key components of this multiplicity problem. After that, this data set is going to be passed to the mixed gate macro. The macro will be called. It will perform a multiplicity adjustment and it's going to generate multiplicity adjusted p-values. But before we get to that, let's take a closer look at the data set. The data set contains 4 rows, 1 row per hypothesis of interest, and for each row we specify several variables. The first variable is the label of each hypothesis, and we can see that they are labeled H1, H2, H3, and H4. The second variable, called family, is the family index. It's equal to 1 for the first 2 hypotheses, and it's equal to 2 for the third and fourth hypothesis. The next variable, parallel, is a set of binary indicators that are used in problems with parallel gatekeepers. In this case, the first family is not a parallel gatekeeper, and therefore we're going to skip this variable and move on to the next variable called serial. Here, using again binary indicators, we can specify fairly general logical restrictions. We can see that the serial variable is not defined. All of the binary indicators are set to 0 for the first 2 hypotheses, and that is to be expected because this is the family that is the gatekeeper. However, when we move down to the third and fourth row in this data set, we see that the binary indicators in certain positions are set to 1. The actual location, the actual position here is very important because we see that for the hypothesis H3, the first position, the first digit in the serial variable is set to 1, and the other 3 digits or indicators are set to 0. That means that the hypothesis H3 will not be tested unless the hypothesis which it depends on, which is the first hypothesis. That means hypothesis H1 is rejected. And when we move down to the hypothesis H4, we see that the second digit, the second indicator in the serial variable is set to 1, which means that this particular hypothesis will not be rejected, will not be tested unless the second hypothesis in this problem, which is the hypothesis H2, is rejected. This is how we define the logical restrictions in this multiplicity problem. And the last variable in this data set is simply defines the one-sided p-value for each individual hypothesis. We're now ready to pass this data set to the mixed gate macro. That is the first argument of the macro. The second argument is the mixture method. The third argument is the component procedure that is applied to the first family and to the second family. In this case, we're dealing with a Hogberg-based procedure, and therefore this test argument is set to Hogberg for both families. The gamma parameter defines the truncation parameter, but only in the first family. We see here that the gamma parameter is set to 0.7, which means that the first family procedure will be truncated with the truncation parameter of 0.7, and automatically the gamma parameter in the second family is going to be set to 1, which implies immediately that the regular Hogberg procedure will be applied within the second family. Finally, the last argument of the mixed gate macro is the name of the data set where the multiplicity adjusted p-values will be stored. We will call this data set ADJP, which stands for adjusted p-values. We will then apply this Hogberg-based gatekeeping procedure by invoking the macro, and the last step will be to print the multiplicity adjusted p-values as shown at the bottom of the slide. The output of this macro is shown on slide 44. These are the multiplicity adjusted p-values for the 4 null hypotheses in this multiplicity problem. They're arranged sequentially. This is the p-value for H1, and then H2, H3, and finally H4. Using a one-sided alpha of 0.025, we can immediately see that the first hypothesis H1 and the third hypothesis H3 will be rejected by the Hagberg-based gatekeeping procedure, and the remaining hypotheses will be accepted. This set of conclusions is of course consistent with the numeric example that we went over a few minutes ago. The next set of slides is going to talk about software implementation issues in R. In this case, as we have done many times before, we're going to utilize the Mediana package, and within this package there's a very useful function called the adjust p-values function. We used it a lot in part 1 of this online training course because this function supports multiplicity adjustments based on a very broad class of multiple testing procedures, and it also supports general mixture-based gatekeeping procedures. Slide 46 shows us what we need to do to perform a multiplicity adjustment based on the general gatekeeping procedure. In example 3, I'm going to carefully walk you through this code. The first line of the code defines the set of raw or univariate p-values corresponding to the 4 null hypotheses of interest. The next construct here defines the set of families in this multiplicity problem. We can see here that the first family is defined as the set of hypotheses with the indices 1 and 2, so that would be H1 and H2, and the second family contains the other 2 hypotheses that are H3 and H4. Next, we're going to define the component procedures that will be applied within those 2 families. They come from the same family of multiple testing procedures. They're both Hagberg procedures. The only difference between them, of course, is that the first one will be truncated and the second one will not be truncated. This will be the regular Hagberg procedure. And to be able to communicate this information to the adjust p-values function, we're going to specify now the gamma parameter. This is a list of truncation parameters for each individual family. We can see here that for family 1, the gamma parameter is set to 0.7, and for family 2, it is set to 1. We're now ready to call the adjust p-values function. We simply pass all of the objects that we have defined so far to this function. This function processes the results and it outputs a vector of adjusted p-values. Those p-values will be printed on the next slide. We see that the adjusted p-values produced by this R function are identical to those produced by the mixedGate macro. This is obviously a very good sign. This could be used for validation purposes. Once again, we come to the same set of conclusions that 2 hypotheses in this multiplicity problem would be rejected by the Hagberg-based gatekeeping procedure, and the other 2 hypotheses will not be rejected. To provide a high-level summary to a discussion of gatekeeping procedures in clinical trial applications, this is the topic that we have spent quite a lot of time on. We started discussing the concept of gatekeeping procedures in Module C, and now here in Module D we've expanded that to a more challenging set of multiplicity problems with arbitrarily complex logical restrictions. However, when we step back and take a look at the big picture, we recognize that gatekeeping procedures are simply an example of multiple testing procedures. This is a subset, a subclass of multiple testing procedures that are specifically designed to deal with multifamily multiplicity problems. So whenever we have a set of predefined families of null hypotheses that are connected to each other using appropriate logical relationships, it would be appropriate to apply a gatekeeping procedure. The key features of a general class of gatekeeping procedures are shown on the slide. First of all, of course, they control the global family-wise error rate across the families. They do it in a very efficient way by explicitly accounting for meaningful hierarchical relationships among the null hypotheses of interest. They are formulated using logical relationships or logical restrictions. And the importance of using gatekeeping procedures in clinical trials has been demonstrated in dozens of phase 3 clinical trials that have successfully utilized this general approach to multiplicity adjustment, and that enabled the sponsors of those trials to enrich, to strengthen the product labels by including relevant key secondary findings in the product label without compromising overall alpha control.